Hello, and welcome back to TechFrame. The roar of heavy machinery is being replaced by the hum of drones and the quiet precision of robots. Forget brick and mortar. The future of construction is being built with smart materials, augmented reality, and autonomous vehicles. These 20 technologies are not science fiction. They are redefining skylines today. Carbon-negative concrete. Traditional concrete is a carbon giant. Carbon-negative concrete flips the script by embedding CO2 directly into its structure during production. Special mineralization processes trap greenhouse gases, turning them into solid stone. This not only makes the material stronger, but actively reduces a building's carbon footprint. From highways to office towers, the push toward carbon-negative materials is changing the environmental balance of construction forever. Robotic swarm construction. Instead of one giant machine, imagine dozens of smaller, specialized robots working in harmony. Robotic swarms, tiny autonomous builders equipped with sensors and task-specific tools, are being developed to lay bricks, pour sealants, or assemble modular components in parallel. This distributed approach drastically reduces downtime, accelerates timelines, and creates resilient workflows where one failure doesn't halt progress. AI-driven design platforms. Architectural design is moving beyond CAD. AI-driven design tools generate optimized building layouts based on parameters like cost, energy efficiency, and material availability. By running thousands of simulations in seconds, they identify the smartest possible design. These tools allow architects to push creativity while ensuring practicality, balancing aesthetics with sustainability and affordability. Robotic surveying dogs. Four-legged robots like Boston Dynamics Spot are finding a home on construction sites. Outfitted with LiDAR scanners and 360-degree cameras, these robotic dogs can autonomously patrol job sites, capture detailed survey data, and relay it back to engineers in real time. They navigate hazardous areas that are unsafe for human crews, reducing risk and ensuring up-to-date mapping without delays. Virtual reality VR immersion. Unlike AR overlays, VR offers fully immersive walkthroughs before the first brick is laid. Stakeholders can strap on a headset and experience the space, checking ceiling heights, sightlines, or accessibility flow. This eliminates costly redesigns and helps clients make informed decisions early. For workers, VR doubles as a training tool, simulating hazardous tasks in a safe environment. 4D printing materials. If 3D printing builds, 4D printing adapts. Materials created through 4D printing respond to environmental changes, expanding, contracting, or reshaping based on temperature, moisture, or pressure. Imagine pipes that automatically expand in freezing conditions to prevent bursting, or panels that bend toward the sun for passive energy gains. This dynamic adaptability makes building smarter without needing constant human intervention. Nano-engineered coatings. Buildings are now armored with nanoscale coatings. These ultra-thin films can make glass self-cleaning, metals rust-proof, and surfaces antimicrobial. By altering material behavior at the microscopic level, nanotechnology drastically extends the life of structures. Hospitals coated with germ-resistant materials or skyscraper windows that never need washing demonstrate how tiny science is solving massive challenges. Bricklaying cobots. Collaborative robots, or cobots, are the middle ground between human labor and full automation. Bricklaying cobots assist masons by holding, aligning, and applying mortar with precision, while humans supervise and adjust details. This man-machine partnership speeds up workflows, reduces strain injuries, and ensures consistency in repetitive tasks without removing the human expertise that still matters on site. Smart helmets with AR HUDs. Hard hats are evolving into intelligent headsets. Equipped with heads-up displays, these helmets project real-time instructions, blueprints, or hazard alerts directly in a worker's line of sight. Combined with voice commands and gesture controls, they enable hands-free access to data on the spot. Instead of flipping through manuals, workers see instructions layered onto their environment in real time. Shape memory alloys, metals that remember. Their original form are being built into bridges and skyscrapers. Shape memory alloys can bend under stress and then return to their initial shape when heated or triggered by electrical current. This unique property makes them perfect for earthquake-resistant supports and adaptive joints, extending the resilience of large infrastructure in disaster-prone zones. Wearable robotics for precision tasks. Beyond heavy lifting exoskeletons, lightweight, wearable robotics are being designed for fine motor tasks like drilling, welding, or wiring. These suits stabilize workers' arms, reduce vibration fatigue, and enhance dexterity. They make it possible for laborers to perform delicate tasks with surgical accuracy, even in awkward positions or extended shifts. Piezoelectric wall panels. Walls that generate electricity sound futuristic, but piezoelectric materials can convert vibrations into usable power. When integrated into wall panels, they harvest energy from environmental vibrations, nearby traffic, machinery, or even wind gusts. The generated power supports low-voltage systems like sensors, emergency lighting, or monitoring devices, creating a building that passively fuels itself from its environment. Smart glass facades. Electrochromic glass facades can shift from transparent to opaque at the flick of a switch, or automatically adjust based on sunlight. By controlling heat gain and glare, smart glass drastically reduces HVAC demand and boosts occupant comfort. Office towers fitted with adaptive facades save millions in energy while offering occupants customizable daylight. Carbon fiber reinforcements. Steel has long been the backbone of reinforcement, but carbon fiber is lighter, stronger, and corrosion-proof. Used in beams, panels, and wraps, carbon fiber reinforcements enhance load capacity without adding significant weight. This makes retrofitting old structures safer and allows new buildings to reach ambitious designs without compromising strength. Real-time structural health sensors. Instead of waiting for cracks to appear, embedded sensors now monitor a building's health continuously. These IoT sensors measure stress, vibration, and temperature across a structure, sending data to a central dashboard. Engineers can detect weaknesses early, schedule preventative maintenance, and avoid catastrophic failures. It's like giving every building its own immune system. Robotics-assisted demolition. Not all construction is about building up. Sometimes it's about tearing down. Remote-controlled demolition robots handle hazardous deconstruction work, breaking concrete, cutting steel, and removing debris in confined or unstable spaces. Their precision reduces collateral damage, speeds up renovation projects, and protects workers from collapsing structures or toxic dust. Hempcrete construction. Hempcrete, made from hemp fibers, lime, and water, is lightweight, insulating, and highly sustainable. Unlike traditional concrete, it locks away carbon and breathes naturally, regulating indoor humidity. Entire eco-villages are being built with hempcrete walls that are fire-resistant, mold-proof, and biodegradable, making it a front-runner in eco-friendly housing solutions. AI-based safety analytics. High-definition cameras paired with AI can now scan job sites to detect unsafe behavior, like workers without helmets or machinery operating too close to humans. These systems issue instant alerts before accidents happen. By analyzing patterns or near misses, AI not only enforces compliance, but actively improves future site layouts for safety. Zero-waste 3D printing with recycled plastics. Instead of concrete, some large-scale printers are using recycled plastics. Waste plastic is shredded, melted, and extruded into structural components with near-zero waste. These 3D printed walls and panels reduce landfill contributions while creating affordable housing solutions. Entire communities could one day be built from the plastic waste we currently discard. Floating foundations. As sea levels rise, engineers are experimenting with buoyant foundations. These floating platforms use airtight concrete chambers to keep entire buildings above water while anchored to the seabed. Already being tested in the Netherlands, floating foundations could enable cities to expand onto waterways, making them resilient to floods and climate change. Analysis of emerging construction technology. The construction industry has long been seen as one of the slowest to adopt change. For decades, methods remained largely the same: bricks, mortar, heavy machinery, and labor-intensive processes. But the technologies now emerging are transforming the field from a high-risk, resource-heavy sector into one driven by intelligence, sustainability, and automation. What becomes immediately clear across these 20 innovations is that they don't exist in isolation. Instead, they create an interconnected ecosystem where AI, robotics, and material science reinforce each other to reshape every stage of the construction lifecycle. From design to demolition, each advancement addresses a pain point that has historically plagued the industry: sustainability as the central driver. One of the strongest themes in sustainability, materials like carbon-negative concrete and hempcrete directly challenge the construction sector's reputation as a major contributor to global CO2 emissions. Similarly, zero-waste 3D printing with recycled plastics and floating foundations tackle environmental concerns by offering scalable, climate-resilient solutions. Buildings are no longer just inert structures. They're part of a broader environmental strategy. Energy efficiency is reinforced through smart glass facades, nano-engineered coatings, and piezoelectric panels, which ensure that buildings consume less and, in some cases, even generate their own power. In effect, future structures will function like living organisms, consuming, producing, and adapting within their environment. Human and machine collaboration. Automation and robotics dominate this new wave, but not as outright replacements for human labor. Instead, they highlight a future of collaboration. Bricklaying cobots, wearable robotics, and robotic swarm construction show that machines can handle repetitive or dangerous work, freeing humans to focus on supervision, creativity, and decision-making. This shift redefines the role of the construction worker. Instead of raw physical strength, skills in managing machines, interpreting data, and overseeing systems will dominate. Tools like AI-driven design platforms and VR immersion push this further. Workers and architects gain superhuman levels of foresight, spotting problems in advance and preventing expensive errors. Safety and risk mitigation. Construction has always been one of the most dangerous professions, and several technologies directly target this challenge. AI-based safety analytics, smart helmets with AR HUDs, and real-time structural health sensors make accidents less a matter of fate and more a preventable outcome. By shifting from reactive responses to proactive systems, these tools ensure lives are saved while projects remain on track. Even demolition, historically one of the riskiest activities, benefits from robotics-assisted demolition, which allows machines to take on the most hazardous tasks. Safety, once seen as a cost, is increasingly becoming an efficiency driver toward resilient and adaptive infrastructure. A fascinating trend is adaptability. Materials and systems don't just endure, but respond dynamically to stress. Shape memory alloys that reset after earthquakes, or 4D printed materials that expand with temperature shifts mark a move away from static construction toward resilience. Buildings of the future won't just withstand their environments, they will interact with them. The introduction of floating foundations pushes the boundary further. It reflects not just technical innovation, but a philosophical shift. Rather than resisting climate realities, construction adapts to them. This represents a profound pivot in how humans conceive of cities in the age of rising seas. Strategic implications for the industry. Taken together, these technologies signal a dramatic rebalancing of cost, time, and safety. Projects that once took years could be delivered in months. Structures that were once resource drains will become energy producers. And job sites that were once dangerous will evolve into digitally monitored, AI-optimized zones of efficiency. But the path forward won't be without friction. Widespread adoption requires heavy investment, regulatory adaptation, and cultural change within construction firms. Traditional contractors may resist, while early adopters seize competitive advantage. Governments and cities that encourage experimentation through subsidies, pilot programs, and regulatory flexibility will likely lead the way in creating futuristic skylines. Conclusion. This analysis shows that the industry is standing on the edge of its most profound reinvention since the Industrial Revolution. The fusion of robotics, AI, smart materials, and sustainability isn't just about faster buildings. It's about smarter, safer, and more resilient societies. The future of construction will not simply be measured in steel and concrete. It will be judged by its ability to harmonize with people, the environment, and the uncertain challenges of tomorrow.